Hey, John here. I just added a README file to the always directory here in these Verilog examples that goes over the synthesizable, let's call them templates or patterns of Verilog that represent types of combinational and sequential circuits. A big thanks to all my Patreon subscribers and thumbs uppers. Thank you for helping me out with this channel. As I say right here, this is a summary of the synthesizable constructs, or maybe we call them design patterns or something like that you can find in this manual here. It's like the first version of an official documentation that says if you write for synthesis, you want to use these particular types of always blocks in order to get them to synthesize into known schematics, okay? So I leave them here with these little copyable buttons here. We can use these as templates when we're writing code, all right? So this all applies to what I've already talked about on this channel, but let's make sure that we're all in sync on how we're supposed to use them so that a synthesized design will behave the same way or close enough to a simulated design when you're debugging it, okay? So, a quick review on combinational circuits. You can create one with a continuous assignment, or you can use an always statement if you want. If you use an always statement, you cannot use pos edge or negative edge, okay? That's not combinational. That's a clock signal for a flip-flop, okay? I just use these. I just @*. If you're doing it any other way, you're trying to get cute and creative, you may be, especially if you're learning how to do things can get very confusing if you don't do this just right. And this is one of these like simple crutches, a rule of thumb. If you do this as your sensitivity list, you're already better off than if you're trying to do everything else absolutely perfectly and some other way. Again, you only use blocking assignments, or should anyway, when you're creating a combinational circuit. Anything else doesn't really make sense if you're using a certain set of design patterns and conventions. I mean, sure, you can break the rules and get things to work, but if you follow a certain set of simple rules, then it'll work more often earlier in your design and debugging than otherwise. So at least that's been my experience, okay? So what do we got here? Continuous assignment to create a multiplexer. Okay, when cell is true, I'm going to use it. I've got a 2-in multiplexer. You got two inputs, B and C, and the output is A. All right, I probably should have named them Q and so on, but you know what I'm talking about. All right, so when cell is true, what do we got? When cell is true, I'm going to assign the value of B to A. Maybe I should have said this in the other way around or whatever. I'm sorry. I'm a dingus. And it just dawns on me that I believe the release date of this video is Dingus Day 2024. So to celebrate Dingus Day, I'm going to leave this phrased backwards like that. So when cell is true, A is assigned the value of B. Perhaps that would have been clearer. When cell is false, A will then be assigned the value from C, and that's exactly what we have here. If we're using the ternary operator like this, and an assignment statement, and this is very common. At least I do this a lot of times. I create multiplexers, in other words, with assignment statements like this. As we all know, if you're going to use an assignment statement, the thing on the left-hand side of the assignment operator has to be a wire, not a reg. And this is how you use the ternary operator like that. If you know C or any of the derivatives that are outrageously common, you've seen this before and you know how that works. If you want to define it using an always statement, and you're going to assign a value in an always statement, you know that has to be a reg, because that's what you have to have on the left-hand side of an assignment operator in an always statement, or an always block, as I like to say. Okay, so here's your @*. If anything that's consumed as an input to this process in here changes its value, then execute this always block, okay? So that would be cell B and C. I mean, if I was to write a quiz for some students, I would say, what are the inputs to this thing? And, you know, the B students might miss this because cell is an input, right? It's consumed in order to answer these questions. So cell is true, A is B, else A is C. General rule of thumb is you use a blocking assignment when you're doing combinational circuits. And you use a non-blocking assignment when you're doing sequential circuits. Now we have two different kinds. We have edge sensitive and we have level sensitive, okay? And it turns out the level sensitive ones are not as, I mean, I don't find them as useful as the edge sensitive ones. I tend to always use edge sensitive sequential circuits when I design my Verilog. And it fits in well with the style that I use that we'll talk about at some point as well. If you want to read ahead on that, if you go to Verilog examples, the style I use, the first time I was able to open up my eyes and understand what the heck is going on, because everybody was mixing the synthesizable with the non-synthesizable code and just writing haphazard Verilog all over the place. If you go to the Verilog examples direct repo that we're looking at right now and click the extra docs, can be found here. Oopsie, that's the wrong one. Documentation resources can be found here. There you go. My Verilog notes. This is kind of a reading list. This is the ICE 40 stuff, and here's these standards that we're looking at. This one right here, 1364.12002 is the one I'm based these examples on we're talking about today. This guy here, Pong Shu, wrote a book. There's a couple of different variations. He's got a system Verilog one. He's got a Verilog one. He's even got, you know, VHDL books and stuff like that. And he uses a style. This was the book that I first finally understood. This thing here, and there's a newer edition for system Verilog, by the way, which you might want to dive into. We'll get there soon enough. He uses a style, and I'll get into it. It's called, what was the official name? It's in papers around the network and stuff. In fact, non-blocking, the guy that writes these papers here, where is it? This Sunburst Design. If you find this Cummings guy over here, he has some good ideas, and he wins awards at conferences and stuff like that. Now, they're 20 years old, yes, but at the time they were important, and they still are if you're just getting started. I've read a number of these papers, completely agree with this guy. He's very much in sync with this Pong Shu guy, as far as I recall. In fact, they probably influenced each other. This is the style that I'm following, all right? Good or bad, I look forward to your opinions as we go. I really do, actually, because I may be wrong, but those two guys make sense to me. I'm just saying, all right? And that's the style I'm talking about if you're already familiar with it. Or if you're not, maybe throw some eyes on some of those papers from Cummings or find a copy of the Pong Shu books, because they'll talk about these. What you do is you take two separate always blocks, an always block that has a sequential circuit in it, and you team it up with an always block that has a combinational circuit in it. And it's this two always block style of design that those two guys advocate for. And if you use that style, and I'll get into it, that's where we're heading someday. If you use that style, then these things naturally fall into play, all right? Or vice versa. I think that, you know, it's all connected, right? So anyway, where are we going with this? Back to, hello, focus. Okay, so generally, I mean, I would say always, okay? If you're going to use the dual always block style that we're heading towards, I find that I always use non-blocking assignments when I write my sequential circuits. Okay, now there is an exception. If you don't use the dual always block thing, you want to save some time or not type so much, you can kind of combine the two always blocks into one big wad, which I've seen people do, but it gets out of hand really quick. If you do that, as things get more complicated, especially when you're just learning, I strongly urge you to use the dual always block style. If you're using the dual always block, you generally don't have a situation where the sequential circuit in your design is complicated enough to require you to have temporary variables that hold values while you're expressing the code in a sequential circuit, okay? And that otherwise you may need that because you might be, calculating a value using multiple statements in a row in your always block, and you might need variables to hold values from statement to statement. And obviously, you would not want to use a non-blocking assignment in such a case because you couldn't, say A equals 1, A equals A plus B, things like that, and want to have them processed in order using blocking assignments, okay? But you can, my point is, if you end up in a situation like that, you would ultimately be calculating a value that would then be assigned to some output reg variable with a non-blocking assignment in that same always block anyway, okay? So, like I said, I never do this. I never need to, but you can. And at some point, maybe we'll throw together an example. I look for some comments below. Show me if you use the dual always block style, when does this ever come up? What am I missing? I mean, I'm not really a great expert in this. I get by, and I've written a lot of circuits with it, and hobby stuff, really, okay? And they generally work. I've never had any trouble, and I've never had to do this, is my point, okay? Okay, so we have edge sensitive, like I said, and level sensitive, all right? So first, edge sensitive. These are the ones I always use. So what do I say in here? Sequential circuit can be defined in always statement that is positive edge or negative edge. Okay, so as soon as you got positive edge and negative edge, we're talking about sequential circuits. We're not talking about combinational anymore, okay? So let's start out with a simple one, and then we'll add like reset signals and stuff like that as we go. So what do we got here? Always, when I got a positive edge on a clock input, and I always call my clock CLK, you might call it C, use a descriptive word so people know what the heck you're talking about, please. Whenever clock goes from low to high, execute the body of this always block. Set A equal to B. You're always going to want to use a non-blocking assignment in these things unless you get to the point where you are doing more complicated stuff in here and know better. Okay, so what is this, right? It's a simple D flip-flop with no set nor reset. Simply, when the edge arrives, transfer B over to A, and we're done. What if I want a synchronous reset? All right, look what's going on in here. We have a pause edge clock, same as we did before. Let's scroll them both on the screen at once here. If you see the positive going edge, you execute the body of this always block. So what happens if I happen to be executing the always block and reset is currently true or high? Then it will do this. It will assign 0 to A, non-blocking. Otherwise, it'll assign B to A. So it's the same thing as this, but if reset is true, we want to reset it. It is synchronous because the flip-flop will only be reset on a leading edge of clock. Now, if you wanted a negative edge going clock, you'd say neg edge, and all the same stuff is still true. If you want an active low reset, you'd put a bang or a tilde in front of this thing and negate it, okay? Of course, a bang would probably be a better choice in this case because reset is, normally it's a single bit and it wouldn't make a difference which way you did it. However, if it had more than one bit in it, you'd have to be more careful about how you express this condition. This is not the subject of today's discussion, but you know what I mean. I say that because down here I use a tilde somewhere. which is perfectly fine if it's only a 1-bit signal. But, you know, a perfectionist may argue otherwise. Okay, so what do we got now? It's synchronous set and reset. No big deal. You just add some more else's in here. If reset is true, you got a 0. If set is true, you got a 1. Otherwise, you propagate the data through. Okay? Now look at the notes in here. Reset specifically is not in the sensitivity list, nor is set in this one down here. Okay? That's what makes it synchronous, because it's synchronized to the positive edge on the clock. The only way this can ever run is on a positive edge of a clock. Therefore, everything and anything that this ever does or accomplishes can only happen synchronized to pos edge of clock. That's what makes this synchronized, right? What else do we got in here? Notice that the assigned reset and set values have to be a constant. Otherwise, this won't work. I swear, as God is my witness, I read that somewhere in one of the IEEE specs. I cannot find it, but correct me if I'm wrong in the comments below. I'm pretty sure this is a thing. But my memory has not been perfect in all occasions, so feel free to check the notes below this video if I'm wrong. Pretty sure I'm right. I mean, I'm 99% sure to give you odds on this thing, all right? That these have to be constant. And the reason they have to be constant, if you think about it, is, you know, like I couldn't say like A non-block C in here, because the latches that are inside FPGAs only have one data input, and they have one clock. Okay? How can, that would suggest that there's a mux in there somehow. If you want that behavior, you're going to have to combine this flip-flop with a mux, okay? You can't do that all at once, okay? Even if the Verilog compiles and runs, you don't have the circuit you think you do if that's what you try to accomplish in here. It may not synthesize this, depending on your synthesis toolkit, is my point. All right, so these got to be constants, because they're set and reset signals that go into a flip-flop that is inside of an FPGA, or even if you go out and buy one in a TTL chip or something. Those are just simple input bits that force the output to become either a 0 or a 1. So you do have to express it that way, otherwise it cannot be synthesized, or at least can't be simplified down to a single flip-flop, okay? Now let's talk about asynchronous set and reset. Now, this one's a little more wonky. Every time I try to do this, maybe this is my hobbyist thing coming in here. I don't have professional experience of years like some people do. Please enlighten me, okay? I look at this as kind of annoying, and no matter what, okay, however right or wrong I am about this example I'm going to show you here, what is true is if you use an asynchronous set and reset, especially if you're going to tie these signals somehow outside of the FPGA in the outside world, I mean, you got to keep in mind the setup and hold times on these things. This isn't just miraculously going to work the way you think it does if you hook these up willy-nilly. This is why I don't do that. I used to try and make this work so that I can reset my circuits and stuff like that with a regular reset line. We'll move forward, I'll show you how I do it. I do it with synchronous sets and resets, if I have them at all, okay? And the way I do this, if reset or set are external signals to my FPGA, I synchronize those values, and we'll talk about that soon enough, to the system clock, and then inside the FPGA, I use synchronous sets and resets on my circuits. That makes my life a lot simpler, and when you go to debug it in the real world, you're not bringing in these random signals. Again, if it's asynchronous, you do have to make sure that you're not violating the setup and hold times. If the set and reset signals are moving on and off too close to the point in time when the positive edge of the clock comes along, all right? Because this, I mean, get real, people. You can't just make your whole circuit asynchronous internally and have everything be perfect if you're using external signals to do all this. Nonetheless, this is how you can do it if you want to try it. This will probably work 99.999% of the time, by the way. But it's the one time when it needs to work and you're demonstrating it in front of a customer or something that it will fail eventually, and you end up with a black eye. So, as I say, it's tricky to follow since it has the set and the reset signals are also in this sensitivity list. Okay? And if you think about it, let's say you're going to write the synthesizing, software, the compiler for this thing. And you see this. Now, I named them appropriately. But if this was just called X, Y, and Z, which one of these things represents the one and only one clock that really is present on a flip-flop? Many of you ever seen a flip-flop that has more than one clock? No. Right? So it's the job of the synthesis tool to try and figure out what you want to happen when you say something like this. Which also is kind of laughably goes back to, remember that Verilog was originally designed for simulation, and not synthesis was not on the horizon until some years later. So this set of rules had to be specified that said, look, when we're doing synthesis, you have to express it this way, otherwise the compiler won't realize what you're trying to do, and it may build the wrong circuit. This is one of the reasons that a lot of people are like, oh, we should be using higher level languages and blah, blah, blah. Yeah, okay, that might be good depending on your project. But if you want to know what's really going on, you might want to take an eyeball down here and then before you use the higher level languages. I've seen people academically fail to use high level languages and accomplish anything because they don't realize what they're trying to, what it means when they try to synthesize it. How do you size the FPGA? How do you know how many resources you can do? What's practical? They have no idea what's going on under the covers, and surprise, it doesn't work. So here's another reason I'm looking at these arcane, ancient, lower-level view of things here today. But once again, I digress. Apologize for that. Okay, so let's assume we don't have setup and hold times issues. What do we got? Every signal in the sensitivity list must be edge sensitive. If I'm doing this, right, with an asynchronous set and reset. And you might think this is weird, but this is the rule, okay? This is where, I need to understand the rules, otherwise it won't synthesize correctly or it won't simulate correctly. So these have to be edge sensitive signals. All of them. So we got the exact same sort of thing we saw above. I inverted the set just to make this interesting, and probably should not have done that because now we got two things going on in our heads at once, violating one of my rules. Only change one thing at a time. But I'm a dingus. Sorry. Okay, so what do we got? Pause edge clock, pause edge reset, neg edge set. So this would be, I have a active high reset, active low set on a flip-flop. Okay, so far so good. You got the pause edge reset, and this matches the same thing we saw up here. If you want to reset it, set it to 0. Now notice over here, the edge direction, pause edge, has to match the polarity of this thing. In other words, if reset goes from 0 to a 1, it's transitioning into its active state. Therefore, it must be active high when you ask in this if else down here. And I believe, if memory serves, that the spec says you must use if else in here. You couldn't use some other construct to do this logic, okay? Because of this comment down here, which we'll see in a minute. Okay, so if reset goes active, that will trigger the always block to run without any regard to whether or not clock went active. That's what makes this asynchronous. Okay? Same thing with set. If set goes active by a falling edge, This will be processed. It'll wake up and it'll run this code in here. And this is the tilde. This might be better expressed with a bang. Let me go ahead and put that in there. That's probably, I think, somebody actually called me out for that once before. Whoever you are, thank you for ruining my recording today. But they're right. Okay, this is probably the better way to do it. Commit, I'm going to just say bang. Because, sometimes your comments are really subtle. Okay, great, good job. Another bad practice. Okay, where were we? Okay. Oh, look, it's better now. So if set is low, false, right? Then bang. It's what we called this when I was at AT&T. An exclamation point. Actually, AT&T called it a ball bat, right? And UUCP and style email referred to that as a bang and so on. Anyway, moving on. If reset saw a positive going edge, it became active. We wake up and we process this. We see it's high. We assign the reset value. If set goes active and it's falling down, therefore it's negative, we need a negative condition for set down here, and we assign the output accordingly. Again, all non-blocking. Okay? Now, the way this has to work is that the final else with no condition is the code that represents what to do when the clock transitions on its active going edge. So the clock to the flip-flop is the signal in the sensitivity list that does not appear in the if-else, if-else, if-else. It's the only one that's not used in these expressions. Therefore, it must be, we can infer is the word that Verilog likes to use. The tool will infer that this is the clock for the latch, or the flip-flop, I should say. Okay? The other ones over here are the asynchronous inputs that are obviously recognizable in these ifs, okay? And it is this last else, the naked else, that represents the synchronous setting of the data, okay? In latching it into the flip-flop. And I mix those words all the time. I apologize, because when I learned all this stuff, I never differentiated between latch and flip-flop. Flip-flop takes longer to say, and it also sounds kind of dorky to me for some reason. Therefore, everything was a latch, and I would specifically have for the last 45 years, would have historically said edge-triggered or level-sensitive latch. Okay, so I'll probably slip all the time when I'm recording. I apologize, but just so you understand what I'm doing here, and I try to make sure that I give you the courtesy of knowing what I know I do wrong, so you don't learn it wrong yourself. I honestly don't think it was differentiated until well after the 70s when I started learning all this stuff, perhaps by Verilog itself, because Verilog does, at least System Verilog, does use the words very specifically where they refer to flip-flops, as I do in the heading here. All these headings are these synchronous flip-flops, and the latches are these level-sensitive things. Okay, we'll talk about that in a minute. Now, let's look at the this asynchronous set and reset thing going on here, and this is why I don't use them. Okay, correct me if I'm wrong, but look at the code above and look at this sequence here. Let's see if I can get it all on the screen at one time without shrinking the font to the point where nobody can read it. Good enough. So here's the code up here, and let's say over the course of time we have this. Let's say the clock is 0 and it becomes 1 down here. Okay, so in other words, clock doesn't trigger anything during during this time period here that is passing. Okay, notice reset goes from 0 to 1 back to a 0 again. Set goes from 1 to 0 here. Now, set going from 1 to 0 is the active going edge here because it is negative, right? All right, so let's take a step back and think about this for a minute. Clock 0, reset 0, set 1. This is, it's quiescent state, and it's sitting there. It's not going to do anything, and it's waiting for one of these to change because clock is a pos edge, and set is neg edge. So these are all in the inactive or false state or value, whatever you want to think of it, okay? Let's say reset goes from a 0 to a 1, and the other ones don't do anything at all. Well, that's a positive edge, so it wakes up, it runs through the thing, reset is true, it assigns A to a 0, and it will reset the circuit at that point in time. Okay? What happens here? Reset is active and set is active at the same time. And set just transitioned from a 1 to a 0. It's a negative edge, so this is going to wake up and it's going to run its code. This is a great example of a priority network, okay? Because reset is checked first, it's going to reset the thing. It won't set it. If you go out and buy a TTL chip, you'll read it, and usually the truth table will tell you what will happen if I set both at once, and usually one will take priority over the other one. So this is actually okay, even though you probably don't want to do it, but that's what will happen because of how we wrote this. If you check the set first and then you said else if reset and did it that way, then the set would take priority over the reset, okay? But as drawn here, this will not set the A value to 1. It'll stay reset. Let's say then reset goes to 0. But nothing else changes anywhere else. Well, that's the neg edge of reset, and that's not a trigger on the always block. So in simulation, what happens here? Well, there's no reason for this to process, so nothing happens there. In spite of the fact that you currently have set in an active state, reset is inactive, and the clock is not ticking. This, I submit, is wrong, but you can't change it. It's not obvious to me how you would make it right, okay? You can't have a neg edge and a pos edge on the same signal. That won't work. That's just not allowed. So, I mean, it might actually be allowed in synthesis. That would be interesting. Again, comments below. I don't use these, so we're getting to a gray area here. I submit that in simulation, because nothing happened here to cause the sensitivity to become active, this doesn't get processed, and this will stay in a reset state. In spite of the fact that set is in fact active right now, and your intent, and this is the problem, your intent is to create an asynchronous circuit. If you go out and buy a TTL chip that is an asynchronous set and reset on a D flip-flop, and you get here, and I actually believe even in synthesis, it will set the output of that latch at this time. The latch, the flip-flop, whatever. Okay? In this sequence of events, if the clock should go true here, the edge that we're sensitive to happens, right? It'll wake up, run through here. It'll find that set is in fact 0, and it will then set A to a 1 here. And that assumes, of course, that the clock ticks, right? Which is kind of screwy. So this is the sort of thing that you might run into trouble with if the synthesis does create a latch with asynchronous set and resets, if your circuit actually asserts both of them at the same time, which is what we have right here, okay? As this thing transitions out of its active state, you have this weird, unknown situation happening here. All right, and that would depend on your FPGA. This may be a synthesis. The synthesis can't know. It can't know that could happen down the road. That's a problem. Okay. Again, asynchronous stuff is just not. I don't use it because I don't have to. It probably would require you to create more circuitry and stuff to make it behave right if you really wanted to do this, wasting all those resources. You're better off synchronizing the set and reset signals if you can, and that may be impractical too, but if you can synchronize them to the clock somehow in another circuit somewhere else in the FPGA, especially if it's like a global signal that you're going to use all over the place, it'd be nice to pay the tax of dealing with the fact that you would prefer and easier to use a circuit that looks like this than one that looks like this and risk it not working correctly when you actually put it in production. Or at least it differing from simulation when you put it into production. Okay, so that's a weird one there. I try to shy away from it. If there's an easy, obvious fix that I have yet to notice, enlighten me. Okay, moving on. Level sensitive latches. I never use these either because just because of the way the style of coding that I use, it is not usually, I mean, I don't think I've ever used one other than by accident, because these are what you end up with when you have these inferred latches like I talked about before, and you'll see that's exactly what we're designing on purpose in this particular case, okay? Now, there are times where you might want to do this. Now, I find that I don't do it very often, if at all. But if you do need one, here's how you do it. You create what is mostly just a regular old combinational style circuit. And you simply say, you purposely create an inferred latch. And by that I mean you assign a value to one of the outputs of the always block in such a way that only sometimes you give it a value. Because this is seen here. If enable is true, you assign the value of B into A. And if enable is not true, you don't assign the value of B into A, and you simply retain the previous value of B that was there all along. And I talked about this at great length in circuitry for the combinational discussion that I recorded earlier, when you do it by mistake and you don't want it to happen. But you can also do it on purpose if you do really want to have what I historically would refer to as a transparent latch. Okay, so another typo down here. Note that as long as enable is true, A will equal B. And I put a blocking assignment in there. How nice. You know what I mean. A will be set to the value of B, which I, used to call a transparent latch. If you buy a, whatever it is, a 74 LS373 or a LS374, those chips were edge and level sensitive style latches. And I think that the official data sheet, at least from National Semiconductor, referred to one of them as a transparent latch, the level sensitive one. So what happens is if you draw up a timing diagram, okay, if you think about it, when when enable goes from its active value, in this case it would be high, to low, on the falling edge of enable is when you stop assigning the value of B to A. So you would argue that on the falling edge of enable in this design, the value of B will be retained or captured and stored in this latch and frozen on the output that we call A. If enable is true and B is going 0, 1, 0, 1, 0, 1 over the course of time, then it's just like National Semiconductor says, it's transparent. It'll just simply, A will then go 0, 1, 0, 1, 0, 1. Because every time B changes, this will execute. Enables 1, therefore A will track B forever as long as enable is true. But when enable goes from true to false on that falling edge is when A latches the value of B at that time and holds on to it. Because if B continues to change after that point, this will continue to get executed, but enable by definition would be 0. NA will no longer be updated, and that's what makes it into a latch or a memory of some kind, okay? Same exact thing we talked about before when we were talking about inferred latches when we don't want them. You can take advantage of this if you want to, and if you do want one, and that's how you do it. So it is these, what 20 years ago might have been referred to as design patterns, okay, are what we're going to use to build circuits that actually do useful stuff, okay? And this is where we're going to build everything up from these. And that's the whole ball game. You throw a module around it, you fill it up with a bunch of these, and there you got your circuits. You got your latches, you got your combinational circuits, your flip-flops. Basically, those are the building blocks of the whole, data processing world. So we're now armed with what we need to build whatever we want that can be built using synthesized code and FPGAs. So from here on in, hopefully we'll make some real stuff. There'll be a few more academic style discussions coming up here when we talk about different ways to parameterize modules, and there's just some other housekeeping stuff that makes coding easier. But as far as actually designing a circuit, the synthesizable guts are all right here. These are what you're going to use. All right, and everything else gets built up out of here. Not bad. Nice and simple, or so it seems at this time. Happy Dingus Day. Thanks for watching. We'll see you next time.